Recording in progress. We stopped on the structure of methane. We are looking at the Bowling theory of the hybridization. How is those bonding is coming together? So if you look at this, we have methane, correct? So methane, we know the CH4. That's a methane. So if you are asked, what is methane? What is the hybridization of methane between carbon and hydrogen? Well, it turns out to be, somebody will tell me what's the shape of this? The shape of this is, if you look at the E central atom, X4, correct? That will be what? The shape is tetrahedral. So the shape is tetrahedral means the carbon, hydrogen, guys, hydrogen, the angle here, the angle is how much? Is 109.05. The angle is between hydrogen at the top, carbon in the middle, hydrogen, that's a tetrahedral, correct? And the angle is 109 degrees. Now, from this here, I can determine the hybridization. So if I have 109 degrees and I have tetrahedral, the hybridization of this, so out of this information I have, I can get the hybridization to be on carbon. Carbon has sp3. sp3. So sp3 has to be what? Has to be tetrahedral. All this information, you have it. So, and then you have from hydrogen just have one S. So one S. So carbon will contribute to the bonding with sp3 hybrid and will clone itself with the orbital of hydrogen 1s. So if you look at the whole thing will be the hybrid here, will be, you look at the whole thing, will be sp3 here, sp3, let me just take this one here. So sp3, this is sp3 dash s. So dash s. So the hybridization of methane is sp3, that's from the carbon, and s. So from the it started with Lewis. Lewis has some problems with explaining the whole theory of hybridization. However, then it will come back to his contribution, because if I know it's tetrahedral, it has to be sp3 on carbon, on the central atom, correct? And the terminal atom will contribute whatever it has of valence electrons. If it's oxygen, will be sp p orbital, empty b orbitals. If it's nitrogen, b orbitals. If it's hydrogen, s orbital. So this is the bonding here, or the hybridization, or the cloning between bonds is sp3-s. S from hydrogen and sp3 from the carbon. And the sp3 means you have shape of tetrahedral. The angle is 109. The angle is 109. Let's take the second one. Take another example. So let's take another example here. Structure of methane. Okay, so if you look at the structure of methane, let's look at the structure of ethane. Well, what's ethane? Ethane is two carbons together. So if you look at this, and we want to have this, it is. You have CH3, CH3. But it's not really like this. It has to be carbon, carbon. And then you have 3 hydrogens in each atom of carbon. So hydrogens here, hydrogens here, hydrogens here, hydrogens here, hydrogens here. This way of writing, called expanded structure, expanded view of the structure, that's expanded. And this one here called condensed. So this is condensed, condensed, and this is expanded structure of ethane. Oops, it's one out. So this is expanded. This now the question is, if I have C, let me just, if I have C and C, and then all those 3, I'm writing in the expanded way. So what your intuition will tell you, you have 1 carbon, correct? And then you have this hydrogen all over the place. So you have 2 types of hybridization or cloning of bonding. One is between carbon, carbon, and the second one between carbon, hydrogen. So let's change the color here. Let's change the color. So here it is. So this is the first one, and this is the second one. All of them, I mean, you can name it. This, all this here, all this, and all this. So it turns out to be between carbon and carbon, we have, remember, this is tetrahedral, and that's another, this is a tetrahedral, AB4, three terminals of hydrogen, and the rest can be determined as another group. So this is still AB4 or EB4, whatever. So this is tetrahedral. So the carbon will be among them is sp3-sp3, right? So the carbon connection sp3-sp3. The carbon hydrogen, though, as we said before, sp3 from carbon and S from the hydrogen. So this is, if you are asked, choices, then it will ask you whether it's carbon, and ethane, or carbon hydrogen. Between carbon and hydrogen is sp3s. Between carbon and carbon, sp3. And it is tetrahedral. It is 109.5 the angle. So I did not. So from the using Lewis structure, I can determine what type of hybridization I'm dealing with. Correct. So let's take another one. Let's take another one. Let's take another one here. How about sp2 orbitals? Well, it turns out to be, anytime I have sp2 orbitals, I have to have the, anytime I have here, let me just, let me have this one here. Let's just change the color. sp2, as I said, sp3, write it down here. This is what? For single bond. Single bond. sp2, believe it or not, this is double bond. SB, this is triple bond. Triple bond. So now if I have SB2, this is a double bond. So the angle here of this one here, let me just switch to another color. It is. This is 109.5 degrees. This is 120, the double bond, correct? And this is 180 degrees. So this is linear and SB. This is trigonal planar, and this is tetrahedral. So let me repeat myself. SB3, it is a tetrahedral, correct? It is a tetrahedral, and the angle is 109.5 degrees. SB2, and this is single bond. SB2 double bond is a trigonal planar, and the degree at the 120, correct? The SB by itself, this is linear, 180 degrees, and the shape, as I said, linear. So from this information, I can build a lot of stuff here. So let me take this one here, and look what's hybridization of the SB2. We did mention this one, correct? So it depends on, look at the carbon. This is for carbon. So if you have a carbon S for SB2, so the two S's and two B's, so it will be one of this here, one of this has to go, let me here. This guys. One of this here, one of the has to go up, correct? So if it go up, then you will have, one will go all the way up. So you will have, and one will hybridize. So you see, one, this is S. Sorry, this is, does not want to. This is S here. And those are the two are B2, correct? One of the B2 is out, this one here is kicked out, although the top to an empty PZ, an empty what? PZ. So this is an empty orbital of P. We kicked out this one here. This one here is making what? It's making the double bond. This by itself on the top is making the double bond. So the B orbital by itself makes the double bond. The SB2 here, those here, SB2 makes what? Makes the single bond, correct? But all in all, the structure of it will be trigonal planar, and the angle is 120. And it is between carbon-carbon. So we have two types of hybridization. Between carbon-carbon, each carbon will have SB2, correct? Dash SB2. So here it is. This is carbon-carbon hybridization or cloning, correct? Now, if I look at the carbon-hydrogen, on the other hand, guess what? It will be SB2 from the carbon, and from hydrogen itself, it has just S. So S. So now we know S, only S. So we have two types of, please. If you don't like it, I said you can leave. Please, be my guest and leave. Not bother. I am bothered when you are talking. I'm not bothered. If you don't like whatever you hear, the door is open. Please. So, as I said, carbon-carbon, each one will contribute sp2, sp2. Carbon-hydrogen, sp2 on the carbon, and hydrogen will have what? S, from one S from hydrogen. So we have two types of cloning or hybridization. Two types. Carbon-carbon, sp2, and this is double bond. The double bond coming from the fact that one, here it is, let me just take some out. The double bond coming from the fact, the side-to-side interaction, this one here, this is here causing the double bond, side-to-side interaction. See here, those are making the double bond, the p orbitals in each carbon. Those are the empty, those filled, and this is when you make cloning them, this is the double bond coming on the top from the p orbital here. Filled, just each carbon will contribute with one, and then you have here two. If you look at this, they have two. So they have two valence electrons. So let's look at this. Let's look at this. This is what we said, sp2, the same thing with the double bond. We have double bond sp2 on carbon and sp2s on carbon hydrogen. So let's do for ethylene. Ethylene is the same thing. Ethylene has the structure of, it is, guys. It is. Ethylene has double bond carbon, and you have hydrogen here. You have hydrogen here. Those of type of question I saw in the past, those are concept-wise. They don't ask you for calculations, just to ask you the hybridization on carbon to carbon on carbon to the other carbon. What's hybridization? So since it's a double bond, so it has to be what? sp2. Since this is double bond here, so your answer is, oops, sorry. Your answer is, this is sp2, right? That's double bond. If you have a double bond, you have to have sp2. That's a must. So your answer in the multiple choices, when they ask, it has to be sp2, correct? It has to be sp2. So now let's look at the other one. We went through all this together. Now, that's just to tell you this is side to side. And there is a multiple choices even in the test bank asking the foundation of the double bond from where? Well, your answer will be, look at this, will be side to side. It is, this is, take this one here. This one here, the side to side interaction yield to double bond. Side to side interaction, not the side. Yeah, the side, but this is vertical. Those are vertical. But when you have the side to side here, this one in the middle here, this is horizontal interaction. Side to side horizontal, and this is from side to side vertical. The interaction vertical will lead double bond, and the sigma bond, the sigma bond single bond is from the horizontal interaction of the two orbitals. So you can see here, ethylene has the same thing here, double bond, and if you look at the two hybridization, here this two, and here hydrogen, and here's hydrogen. So you have sp2, this one sp2. So the interaction between carbon sp2. Carbon hydrogen is, this is S. So it will be sp2s, and those are two will be sp2, correct? And the angle is 120 degrees. The angle is 120 degrees. So look at this again. So here it is. Now we are looking at sp orbital. Sp orbital is linear, correct? So we said sp orbital here Anytime I have SB, I have what? I have the shape is linear and the angle is 180 degrees. So linear, and the shape is this, the angle is 180 degrees. So what happened in SB? So you have one sigma bond, SB, SB. So how many we have? We have 3 types of bonding. One is between carbon and carbon. So carbon and carbon, you have carbon and carbon, you have carbon and carbon here. This is SB to SB, hybridization or cloning, correct? But then you have 2 double bonds, 2 empty, or filled interaction of double bond. One is the Z1, correct? And this is BZ on the top, BZ. And one is the PY. And this carbon is PY. So PY here. So when they interact, the 2 ones here. So this is the first single bond, side to side. And this one here, the second one is here. So you have 2 double bonds and 1 single bond. The 1 single bond is made of SB-SP hybridization. The one in the top will be SB. If that's hydrogen, will be 1s. If that's oxygen, will be B orbital, depending what's the valence electron, what's the atom is connected to carbon. So this is the way you can think. If this is the case, this is B orbital. This is empty. That makes the double bond between the triple bond. So let's look at this again. So, and here, can you see it? This is your SB-SB. Maybe I will just put it up a little bit. You can see it much better. So you can see it now. Now, this is the carbon-carbon is SB-SB. Carbon-carbon is SB-SB. And then the double bond, you have the BZ on carbon, as it's not taken by anything. And then you have the sideways, correct? So this is, and then you have the hydrogen will come on one of the, you have, this is ethylene, this is ethylene, acetylene, this is C2H4. But if I look at acetylene, it will be double. This is the structure of ethylene. So let me take this one here. What will be the bonding of beryllium hydride? Beryllium hydride. So we have beryllium here. Let me just take it out here. Okay, so if I look at this, beryllium, although it's a metal, but sometimes can make. What will be the hybrid between beryllium and hydrogen? Somebody will tell me? What will be? It is linear, correct. This is linear. So from this, I can tell this angle is what? 100 what? 180 degrees. Perfect. So linear means we have hybridization is what? SB. So this is SB. This will come with 1s. So the hybrid here is I have SB dash S. S from hydrogen, and the beryllium will have SB. So can you see that? Yes. Correct, because that will dictate what the structure. So the shape will dictate the bonding. Because SB is dictated to be linear. SB3 will be tetrahedron. And SB2 will be trigonal bland. SB always single bond. SB2 double bond. SB will be triple bond. SB3 a single bond. SB3 single, SB2 double, SB by itself that's is a triple bond. But here we have only single bond. We don't have triple because hydrogen is exception for the rule. Correct? But still it's SB though. It's still what? SB. That's the linear point. So let's look at another one. Okay. Hybridization of nitrogen and oxygen. Well, it looks like from nature, we don't know why. Hydrogen, always single bonded, correct? When it comes to oxygen, then though, let me just, when it comes to oxygen, it's very unique. Oxygen always will have double bond, believe it or not. Oxygen connect itself most of the time, double bond, and hybridization of the double bond is sp2, correct? Double bond will be sp2. Nitrogen, on the other hand, from nature, that's by nature here, likes to be in triple bond. Triple bond will be sb. So you can tell on carbon, on the other hand, if you look at the carbon likes to be single bonded most of the time, will be sb3. So sb3 is single, sb2 is double, sb is triple. Correct? It's triple. Are you following me here? Now I can go further and say let's look at some of this here. Let's look at here. Let's look at CO2. Let's look at carbon dioxide. Okay, so let's look at carbon dioxide. And this is very famous questions even in the test banks. So this is, so what is the hybridization or cloning on carbon with oxygen? So it turns out to be, this is what? Linear, correct? This is linear, AB2 or EX2. So there's no lone pair, that's linear. So this is linear here, correct? The angle is 180. This is angle here from between oxygen, carbon, oxygen, it's 180 degrees, correct? Well, it asks yourself, what's wrong? If we know linear, so then the carbon here will be what? When we said linear, will be what? SB. The oxygen, on the other hand, is double bonded, so the oxygen will come as SB. Oops. Sorry. So here it is. We have this. So this is two electrons, and this is linear, 180. So it's not linear, but it has to be linear. So 180 degrees. So because this is linear, the carbon tends to have always SB to make linear stuff. The oxygen makes what? Double bond, SB2. However, the oxygen, since that's the hybrid, but the oxygen here does not contribute with the whole oxygen. It contributes with its it is sp2. but the interaction is not SB, SB2. You have to watch for this. Oxygen does not really hybridize itself fully. The terminal central atom does hybridize itself. This is correct. However, this one here is not really SB2. It connects itself to the p orbital of oxygen. So the orbital of oxygen, if you look at the oxygen, is valence electron 2s2, 2p4, six valence electrons. Correct? So one of those unreacted or less reactive valence electron will come and couple itself with the carbon to make the double bond. So one of them here, the p orbital here, the Bz, for example, will make with one of the carbons. So you will see those carbon makes first a single bond, but then those here, the interaction is between those two, in this and this, the p orbital, to make the double bond. One, not between this and this. So those are the p orbital between carbon. So it will be SB, B, Z, SB, BZ. So SB, B cloning between carbon and oxygen. So SB is the carbon, and the oxygen will contribute with side-to-side overlap with its available p orbital, correct? So let's look at some of the example here. Look at some of the examples. Nitrogen, I say it's always triple bond, loves to be in triple bond. And whenever is any nitrogen, you need a lot of tremendous energy when they react exothermic. And most of the nitrogen compounds are highly explosive, very highly explosive, because their triple bond is very stable. When you break it down, it brings you a lot of headache with it. So the nitrogen and oxygen is double bond. Oxygen, most of the oxygen is in double bond. So now here is just to tell you how the whole thing is, the overlap, sigma and pi bonds. So side to side horizontal interaction overlap, let's bring you sigma. Horizontal, side to side horizontally, that's sigma. The pi will come from the overlap from the what? The p or the p unused p orbitals. It has valence electrons in it. The side to side vertical interaction. So sigma is horizontal, and the p orbital is vertical. Here, just give an example of CO2. Correct? Can you see it? So carbon to oxygen here. This an oxygen. Oxygen has Bx and Bz, correct? So the unused here is By. We can't say Bz. It does not really matter. So here it is the oxygen we contribute with one is not reacting. One of the Bz is connected to carbon, correct, to make this sigma bond, and the B side to side will make the double bond. The double bond between side to side. Can you see them here? Let me just do that for you. So here, if you look at this and this is a double bond, correct? And for carbon here and here, there's another side to side. All those are vertical. Even that does look like this for the y-axis, but those still vertical, not horizontal. The horizontal one, that makes the sigma bond here. That makes the sigma bond. So let me take it out so you can see it again. So visualize the whole thing. So you have pi bond between carbon and oxygen, between the p orbital of oxygen and the empty orbital of carbon, the p orbital, and then the same thing with the second oxygen, and the whole thing here is still the sigma bond is made of Sb2 for on the carbon, Sb2 carbon. This is This carbon dioxide, no, that's Sb, sorry, not Sb2. That's linear, correct? SO2 is linear, so this is Sb. So if I don't know the structure, I go and look at the formula of the shape. What's the shape of CO2? This is linear. So it has to be what? On carbon, I have to have Sb. So here it is. So just ask yourself here, carbon is, because it's linear, so it is linear here. So because it's linear, then I have to have carbon is linear. This is Sb hybrid. And then the unused p orbital of oxygens will make the double bond. Okay, so as I said, those questions in the test bank and in the final exam are made concept. There's no calculations or anything, just concept. Now, what we have here, if you look, this structure here will have, you tell me what the structure of this. This is linear, correct? And this is 2 electrons here. Okay, so let me take the other one here out. Okay, so this is what, again, if this is your central atom, correct? This is the terminals. So this is E, no lone pair on the carbon, EX2, and this is what, as you said, linear. That's correct. So this is linear. So now, because it is linear, sorry about this, I'm writing with the mouse. So the angle here between carbon and nitrogen is how much? 180 degrees. So 180 degrees. So what will be the hybridization on carbon? Central atom. That's our central atom. What will be the hybridization? It's linear. Will be what? Sb2, Sb, or Sb3. We said, let me repeat. Sb3 is single bond. Sb2 double bond. Sb triple bond. So this one will be what? On carbon has to be Sb3, correct? Has to be Sb3 on carbon. And then whatever on nitrogen, the same thing is to look, will contribute, because the terminal atom will contribute with the p orbitals, same like hydrogen, the same like oxygen. They don't contribute with the whole thing. So this one will be here. This is Sp3, and this is an unfilled p orbital, whether it's X or Y or Z, whatever you name it. I like to put it Z. So S, write it again. Sb3 p orbital. You don't have to specify where that really is. Can be X, can be Y, can be Z, but I like to see BZ because that is from the top vertical. So that's, I can put this one here Z. So vertical interaction. So you have two double bonds and one single bond. And this is the hybridization between those together. This is sigma is made of this making sigma bond, and the interaction with the BZ here with the unfilled of the PY of the carbon will make the two double bonds. So, and as I said, this is linear. From the linear shape, I can determine the angle is 180, and therefore it has to be triple bond. So make yourself a piece of flashcard. SB linear, angle is 180, and this triple bond. SB2, this is trigonal planar, correct? The angle is 120, and it's a double bond, correct? And then sp3 is tetrahedral, 109O5, and it is single bond. Make sense? Okay, guys, good. As I said, those are coming as a concept for us in the test bank and in the final exam. So they'll ask you, what is the shape of this molecule inside? I mean, inside what is the hybridization or cloning of the bonding inside this molecule? So always the central atom will take first priority. The terminals always contributing with the p orbital. If they are central atom, not carbon, then yes, then you look at the whole picture. So, but since we use carbon as an example, so carbon will have the sp, sp2, sp3, correct? So now the last topic, which is the most interactive topic, and you can see it, it's not covered inside ACS exam, by the way, guys. It's not covered. So if you are asked for this, I don't think they come. But the molecular orbital theory, one of the best, even better than hybridization, it's really feeding the hybridization. This one show you the molecular bonding and non-bonding orbitals. So it does really show you in details. So it shows you that the bonding as orbitals. If they are bonding, they have the same. See here, they're adding themselves up. If they are anti-bonding, they subtract themselves. Like you have two waves, two orbitals as a wave, as electron density found in this wave. So if they are anti-bonding, means they are not bound to any. They are orphans. They're staying in the space without any interaction with the other valence electrons. But if they are reducing or contributing to a bond, then they will add themselves up. You can see those waves. Now, we see this one here, or do we see, or we will see? Well, it depends. All these mathematical calculations, by the way. Nobody has seen this, but this is just based on the statistical and mathematical calculations. So, this is the diagram here of hydrogen, correct? Now, hydrogen has one S, correct? One S1, one valence electrons. When it comes to two hydrogen will come together here. If you look at this, hydrogen will come here with one S. This is one S. This is one S here. See the one S here? This is one S. This is hydrogen. So what's happened is this will combine those two from two hydrogen atoms will combine themselves. So sigma bonding, this one down called bonding, because they add themselves up, correct? And in the top is sigma star or non-bonding. Those are non-bonding. They don't add themselves up, non-bonding. But since we have non-bonding, correct? Since we have only two, each hydrogen will come with one electron. So you can see this is one here. This is the second here. So hydrogen will have one S2, correct? This is the molecular orbital of hydrogen. So those are in the sigma, correct? Sigma means sort of single bond, and the pi is double bond. So you can see thus hydrogen will end up having what? Double bond. And I added this one to you here just to see it. Let's look at nitrogen, oxygen. Well, oxygen, the valence electron of oxygen, just to know, valence electron of oxygen is 1s2, correct? That's not the valence electron. 2s2, 2p, how much? How much is it? 4, 6, correct? In the 6th group. So this is valence electrons. We are interested in this valence electron. We are not interested in this. This one called core, very close to the nucleus. So we are not interested in this. Now look at this. We have each oxygen will come up with 2s2, 2p4, correct? So the 2p has 4, the 2s has 2s from this oxygen. 2s from the second oxygen, 2s here, 2 electrons, and the 2p4. So now it looks like the s will make the single bond. So s's are making what? The single bond. So here the s will split in s, this time 2s, not what we have in hydrogen, 1s. This is, in hydrogen we have 1s, 2s. So, and we have 4, this full, correct? This is 2. So 2 and 2, 4. 2 here and 2 unbonding. So here it is. So oxygen O2 has a molecular orbital of sigma 2, correct? S 2. This is the bonding one, which is those here. Now I include this one here, which is sigma 2, 2s. But this time I will add star. This means this is anti-bonding, higher in energy, anti-bonding, correct? Those are higher in energy. So now the 4 one, they will start splitting. They will start what? Splitting. So here it is. Sigma, they'll make a sigma here at the bottom with 2. The sigma on the 4 oxygen is empty. Then you have that sigma, sigma, single bond. Then you have the by the double bond. This is Bx and By. We can take this one out. See here, Px and Py. So those are 2 orbitals here. This is Py, and this is Px. So we have 4, 4. We have filled those 4. Those are 8, correct? 4. And here's 2. The sigma bond here. Those are 6. And the 2 is coming by themselves. That's anti-bonding, higher in energy. So those are by themselves. That will give us, from this, I can tell that oxygen. Oxygen is what? Paramagnetic. Para what? Magnetic. Now, if you look at if you look, guys, at the Lewis has difficulties in the 2 making bi-bonding, anti-bonding of the bi, non-bonding bi-bond, but 2 valence electrons parallel to each other, not coupling with each other. This is called paramagnetic. On the other hand, if you look at the oxygen, at nitrogen, totally different story. Look at this. I have S is 1s2, correct, for nitrogen. 5, 2s2, correct. 2p3. So this is our valence electrons, 5, correct? So this is the S. We are not interested in this. This we can neglect. This one we are not interested in, the 1s. That's the core. It's called what? The core. Very close to the nucleus. It's not really interacting with anything. The nucleus is attracting it like a magnet. So it's not moving nowhere. So the 1s2, the 2 valence electrons, they are really, it's called core. They have negligence of importance, nothing. So this is called core here. So what here is the valence electron is 2s, and 2p. So how many we have? Each one will contribute 5. So we have to accommodate 10 long, what? 10 electrons, correct? 10 electrons. Now, if you look like this, so this is 2s, 2s2, correct? This is 2s2. We are accommodating this. And this is 2b3. See here, look at this. This is 2s2. This is 2sb3. This is 2b3. Can you see that? So now we can have reduce first the pi, is the opposite for opposite. We reduce the pi bond, correct, from each. So from those we have what we said 3, and the 2 s's are here. Those are single bond. Those making single bond here. This is our single bond. Single bond, correct? Now, if you look at this, if you look at the sb3 here, it has 3 valence electron. It has 3. So take those 2 from each. That's 4. We have how many? We have 6. So 4, and then this here, the non-bonding. This is bonding here, correct? The non-bonding empty. The sigma non-bonding empty, and the 2 left is sigma 2pz bonding. So they have 2 electrons. So nitrogen is predicted from the molecular to be what? Para or diamagnetic? Is what? Diamagnetic. See here, with the Lewis, we have a problem with Lewis theory here, paramagnetic. So it cannot predict. It cannot predict the diam or paramagnetic, and this is a physical property. Will tell us if the element is attracted to magnetic field or repelling the magnetic field. So nitrogen is what is not attracted to magnetic field. Para, yes, it has a 2 unpaired electrons. So you will see those are all those are empty. Now, if somebody will ask you this in the final exam, or I'm not asking those in the quiz. How this is molecular theory is by far is the modern bonding theory, which is really based on calculations, and you can see how nice they can predict if the interaction is diamagnetic or paramagnetic in single bond or triple bond or double bond. So you can see this. So last thing here, and let's see. Sure if this is taken or not. Maybe it's not taken, but it's okay. Summary. I'm trying, if we finish, then you can go and then to the, I don't know if we have a, hold on. Don't see any. So that you go and then put your name for the extra credit, but I don't see anyone outside. So a summary. Organic chemistry, we talked about organic chemistry, we talked about the hybridization, cloning, and we talked about how the Lewis started doing the molecular structure, predicted a lot of stuff, especially the residency of the valence electrons and the shape of the molecules as well, correct? However, he failed in some areas when it comes diamagnetic, paramagnetic, and he did not grasp the hybridization, the cloning, how those bonding are formed. But his contributions, nevertheless, was and is and will be the best contribution, really. So because he opened up the door for the new modern molecular orbital theory, which is really tell us more about this bonding, means they are interacting, and then non-bonding, there is orbital empty, correct? So you can extend, you can add to this and make more compounds. So you can calculate theoretically how much you will add to those empty ones. Remember the empty ones here, we have them, empty orbitals, anti-bonding, you can add to them. So this is the molecular orbital will not go through if Lewis did not really contribute. Lewis contributed tremendously in this indirect, but then he stopped short on explaining this hybridization and diamagnetic, paramagnetic, some of the physical properties. Sigma bi and sigma is always coming from the fact that you have a single bond, which is the sp hybridization. Bi is coming from sp2 hybridization, which is trigonal planar, and sb is linear, and the sp3 is tetrahedral, which is SB is we said the sp3 is a single, correct, tetrahedral, and the sp is triple. The sp is triple bond. So that's a nitrogen is loves to have a triple bond. Oxygen loves to have single bond. Fluorine, all the hydrogens, they cannot, in a very rare situation, they can have this the double bond. Triple bond is impossible. So they love to be in a single bond. They're very active single bond. So this is ammonia has NH3 hybridization sp3, and then whatever is the atom is hydrogen will contribute with the p, with the s, oxygen with the p orbitals. Whatever the terminal is will have p or s orbital contribution to the central atom. We are always interested in the central atom. So this is the whole thing here, and I will stop here.